Okay, let's turn things on here. Um, we don't have any homework due tonight. Yay. So the next homework is not due till Monday the 10th. That's that homework on surfaces, which is really short. And I think there's only like 5 questions, maybe. And I think it's basically identifying surfaces, which you can use this quadratic surface cheat sheet, right? So did y'all bring that back today? Because we're going to use that today. So you don't have to memorize this table. Don't think you're responsible for memorizing this, okay? But it's a handy reference sheet to pull out when you're looking at some unusual equation in 3 variables, right? Well, it's got to be a quadratic equation in 3 variables means each term has degree at most 2 in the equation, and then that's when this sheet is helpful. We're going to use it again today as well. And we're going to start talking about today functions of several variables. So this will actually be a little bit of mixture of our knowledge of surfaces, and then your prior knowledges of functions of a single variable from many courses, right? Okay, especially calculus 1 and 2, which where you study extensively functions of one variable, and so you really know those very well. And so we're going to extend that knowledge to functions of instead of just one variable, functions of several variables, but in particular 2 variables, because that's what will generate when you graph them, those functions. That is what will generate surfaces in 3-dimensional space, right? Which is the subject of the course. So that's what we're going to talk about today. So a lot of that's going to seem familiar, as I mentioned, because it's really just an extension of functions of one variable. So the concepts that you concentrate on for functions of one variable, we're going to concentrate on the same concepts, except just extend them to 2 variables. So a lot of the terminology will seem really familiar to you, if not completely familiar to you. Okay, let's see. I don't think I have any other particular announcement here to make so far. I don't see anyone who was not here last time. So you guys all have your test, right? I'll try to see if I can stick closer to the podium today and to make the tape better. I didn't look at the tape last time, so I don't know if the sound was bad because I kept stepping over to the screen, and I don't think this microphone on the PC will pick that up. I do have a headphone microphone, but it's so awkward to wear that I don't like to wear it. Okay, so I'm going to switch over to the notes now, and we're going to dive right into this topic, functions of several variables, right? So again, we've been talking about, there's a lot of text written into these notes. So if you're downloading the notes, you can read the text. I can't repeat all of this in class. I can't read all this verbatim back to you in class, but I'll mention most of the things that are in the written text in the notes. But all right, so last time we were talking about graphing surfaces of equations with 3 variables, right, in 3-dimensional space. And one way that you get equations in 3 variables in practice is by looking at functions where you have 2 input variables in the function, okay? So again, in calculus 1 and 2, you're dealing exclusively with functions of one variable. That is, you have an input variable, usually you label that x, right? Okay. And then you have some formula or some rule, right, that you insert x into. Could be a formula, it could be a graph, though. So you insert x into your function rule, and then of course you get an output value, right? Usually labeled y from your function rule. Now, remember, the purpose of functions in practice is to take a quantity that we know that or that is easy to measure, and then we apply a rule to that quantity, and that allows us to measure or determine a quantity that's not so easy to measure. Okay, so that's the practical purposes of functions, right? You take a quantity that you can measure easily, and then you have this rule that you can apply to the quantity, and that allows you to discover the value of a quantity that's not so easy to measure. Okay, and in function terminology, the quantity that you know, or the quantity that's easy to measure, is usually called the input quantity. Again, normally labeled x, and then the function that is not easy for you to determine, physically easy to determine, but you can determine it from your function formula or your function rule. That's called the output quantity, and that's usually labeled y. Okay, of course you can change the variable names as you wish, but the standard variable names are x for the input and y for the output. Now, of course, that works great in lots of situations, but in many instances, if you're looking, in many instances, we're looking for output quantities where there's not a single input we can use to determine the output. Okay, sometimes we need multiple inputs. We need to know or measure multiple quantities to determine the output, the quantity that's difficult for us to measure. Okay, and so you get functions with not just a single input, but functions with multiple inputs. Okay, so we're going to look at it specifically, right? Functions with two inputs, right? We need two quantities that we know or that are easy to measure, that we can use to determine the value of a third quantity that's not so easy for us to measure physically. All right, and so we're usually going to label the two input quantities x and y, but you don't have to label x and y. And the output quantity will often label that z. All right, and so if your function rule is a formula, then notice you're going to get an equation with three variables in it, right? X and y, the input variables, and z, the output variable. So you get an equation from the function with three variables, and of course, then you can graph that, and in 3 dimensions, you get a surface, right? Let's take a look at a simple example of a function in two variables. So this is very simplified, just to illustrate the concept to you. Not that it's a difficult a concept to illustrate, right? But I want to make sure that we're clear on it. So here's an example of a function of two variables. Suppose you want to know the volume of a right circular cylinder. So here's a right circular cylinder drawn on the screen, and we're trying to discover the volume of that cylinder. Okay. All right. So imagine that for a moment, right, that you don't know anything about geometry, but you've got this cylinder and you're trying to figure out how much it can hold, right? Okay. How much of a quantity it can hold. Well, notice volumes are not so easy to measure, right? Those are things that are not easy to physically measure. I mean, you could measure the volume of your cylinder by, I guess, pouring some liquid into it, right, and then pouring that back out, correct? Okay, but it's not something that's just trivially easy to measure, right? The volume of a cylinder, okay, or any sort of three-dimensional container, right? Not easy usually to measure the volume of that directly, right? However, in a cylinder, okay, it is easy to measure certain things about the cylinder, right? Physically easy to measure. You can measure the height of the cylinder quite easily, right? Okay, because that you can do with a tape measure, right, Elijah? So that's pretty easy to measure physically. And the radius of the cylinder, that's the radius of the circle that's at the top and the bottom of the cylinder, right? That also is easy to measure because you can also just measure that with a tape measure, right? Okay, so see in this picture, there are two quantities that are easy to measure, the radius and the height, and but one quantity not so easy to measure, the volume, all right? But now, fortunately, okay, from geometry, right, we know there's a rule that we can use if we know the radius and the height, easy to measure, right? There's a rule, a formula we can use, right, to discover the volume, okay, which is not easy to physically measure. See, this is how functions work, right? Okay, again, a function is a process or a rule, or often in the form of a formula, right, where we can take quantities that are easy to measure and use them to determine a third quantity not so easy to physically measure. right? Of course, the function formula in this example is this famous one, right? Okay, the volume of the cylinder is going to be pi times the radius squared times the height of the cylinder, correct? So see, these are your two input quantities in this function, right? These are the things that you can measure easily, right? And then you put them into this formula, and of course you get this third quantity that's not easy to measure physically, right? Okay, but fortunately we have this nice formula that allows us to determine that third quantity. Okay, so the volume here would be the output, right? That's what we're trying to figure out. Not easy to measure physically from the quantities that are easy to measure physically. But see, notice this is a function of two variables, right? Okay, because you need to know our two inputs, because you need to know two things, right? For a cylinder, you need to know two things, right, to determine the volume of the cylinder, right? So you get a function with two inputs, and then the output volume. So if we relabel if we just make this simple substitution, right, and relabel the radius and the height as x and y, and then label the volume as z, of course we can do that, right? Then of course you're going to have a formula in x and y and z, right? Or you're going to get an equation in x and y and z. And so here it is, right? Z is equal to pi x squared times y. And so if you try graphing that, you're going to get a surface, right? Okay. That is not going to be a quadratic surface, though, Elijah. Why not? So it's not going to look like what it may look like, but it's not going to be one of the things on this table. So why is that? Z equals pi x squared y. Ignore the middle for a moment, right? Okay. Z equal pi x squared y. That's an equation with x, y, and z. But if you graph that y, you're not going to get a quadratic surface from that. It's not because y is not to the second power. It's actually because y is to the first power, which you're going to tell me is not the second power. That term, pi x squared y, is not quadratic. It's degree 3, okay? Because when you measure the degree of a term, you add together the exponents of the variables that are multiplied together in the term. So have x squared times y. So the exponents are 2 and 1. You add those together, you get 3. So that's a third degree term, not a second degree. Cylinder. Two quadratic surfaces. No, not necessarily, right? Okay. They do have quadratic surfaces, their equations do have 3 variables in them, though, right? Okay, so that is correct. But this equation also has 3 variables in it. It's just that this term is considered third degree, okay, when you add together the exponents there of the x squared and the y. In quadratic surface equations, David, notice if you look at all the terms, they're only degree 2 at most. Okay, so this won't give you a quadratic surface. It does give you a nice surface, though, when you graph this. When you graph this equation, I think I've got the surface graph there. There it is. Okay, so that's just a piece of that surface, and that if you look at that, you'll see that doesn't match any of that doesn't in fact match any of the quadratic surfaces. Okay, does have some sort of quadratic shapes in it, though. That looks, notice that edge there looks like a parabola. This edge in the back also looks like a parabola. I'm not even sure that's okay. Not certain of that. Okay. No, maybe that is true. We'd have to think about that more closely. All right, so here you have an example here of, again, a function, right? This is a function because you've got your 2 inputs determining your third output, right? Okay, your 2 inputs determining your output, not third output, but your 2 inputs determining your output. So this is an example of a function. And so to put this in function notation, we could give this function a name. our favorite names for functions is x, right? Okay. And then, when you're using function note is f, I mean, right? And when you're using function notation, you inside parentheses, you like to put the input variables, correct? But this has two input variables. So inside the parentheses here, we have to put both x and y. So in calculus 1, you would just have f of x. That's the way you read that, f of, correct? So in calculus 1, you would have just f of x because our functions in calculus 1 usually only have one input. But here our functions will have two inputs. So we have f of x, y, not just f of x. And then our output there is still z, right? Okay. So f is the name of the f there is the name of the f is the name of the function. Now, because in these functions of two variables, you have to have two inputs, right? You have to have a value for x and a value for y. You can think of your inputs as being a point on the plane, the xy plane. So, in calculus 1, since you only have one input x, right? You think of your inputs as just being a number on the x-axis. But since our functions of two variables have two inputs, we will think of our inputs as being a point, right? An x and y point on the xy plane. Okay. So, of course, right, when you're graphing this function, you're thinking of your inputs as existing on the xy plane. You can't really see the xy plane very well in this picture. I guess the xy plane is across here, right? Something like this. So your inputs there are the points in the xy plane. And then, of course, your output value is a single number. It's just, of course, a number on the z-axis, correct? Now, functions of two inputs, functions of two variables, they have domains just like functions of one variable have domain. What is the domain of a function in calculus 1 and 2? What's the domain of a function? Can y'all define that for me? Doesn't have to be a perfect definition. Yeah, let's stay away from the word range, okay? Because functions also have ranges, right? Okay. But the domain of a function is the set, right, of x values, right, that you can input to the function, right? Okay, for which output values exist, which is what I think you said, right? Okay. So it's the set of all numbers on the x-axis, right, that you can actually input to the function. The range is the set of all y values you get when you input every possible x value into the function, okay? So for functions of one variable, the domain is a set along the x-axis. For functions of two variables, however, the domain will be a region because it's a set of points in the xy plane, okay? Notice that when I graph this function, when I graphed this function, I didn't do a very good job of graphing it because I make the domain look like it's the whole xy plane. But the domain of this function is not really all the xy plane, right? Because remember, this gives you volume of a cylinder based on the radius and the height of the cylinder. But radius and height of a cylinder cannot be negative, right? So your x and y values can really not be negative in this particular function. So the domain of this function is not the entire xy plane. It's really only the first quadrant in the xy plane because you want your both your xy coordinates to be non-negative. Okay, so here's a graph of the domain of this function. It's just this portion of the xy plane. All of these points we can use as inputs to this function. But when I graphed it, I didn't limit the domain at all, right? I didn't restrict the domain. So that graph has been made, that surface is above the entire, is above and below the entire xy plane. So one thing we will have to concern ourselves with, just like in calculus 1, this is important. One thing we will have to concern ourselves with is domains of functions. We have to be careful about that. Now look, you can extend the idea of functions of multiple variables to more than two variables. So multivariable calculus, which starts with calculus 3, will also concern itself with functions of several variables, possibly more than two. Okay, so here's an example. I don't know what this function is all about, but here's an example of a function of three variables. Here we have x, y, and z as our input quantities, right? And then we're calling the output w. Of course, we cannot graph a picture of this function in three-dimensional space, right? Okay, so no way to make a picture of this in 3 dimensions, but this could be certainly a useful function. All right, so we often deal with functions of multiple variables. Just unfortunately, when we start getting more variables, we start losing our ability to visualize them very well. Okay, that doesn't mean though that we cannot apply calculus to them. All right, okay, so calculus exists independently of graphs of the functions, right? Okay, so we can still certainly do operations with this function, including do calculus sorts of things with this function. It just gets harder to visualize what we're doing on paper. All right, so here I have a bunch of functions. These are just abstract functions, so they don't really have any physical purpose, I don't think. Let's talk about what the graph of these functions would look like. Here's where your cheat sheet now is going to be. Here's where your cheat sheet now is going to be useful to you, because I think all of these turn out to be quadratic surfaces. All right. So here's my first one. Z is equal to x squared plus y squared. All right. Notice that so you can sort of ignore there the f of x, y. That's just modern function notation, which is going to be useful to us in the class, but in terms of thinking about the graph, it's not useful to us. So let's just drop the f of x, y for a moment and just write down this equation, z equal x squared plus y squared. So there you just have an equation with three variables in it, right? And that is quadratic, Elijah, because the degree of each term there is at most 2. Fortunately, here you don't have any variables multiplied together, so you can just read the degrees easily. This is degree 1, this is degree 2, this is degree 2. Okay, so this is a quadratic equation. All right. So when you graph it, you're going to get one of those quadratic surfaces. Let's rearrange it so that all the variables are on one side, because that's kind of does that make it easier to? No, I don't think so. Can we discover this one already without? We don't need to put all the variables on one side, right? Which form does this look like? Yeah, this is elliptic paraboloid, right? So when we graph this, we're going to get an elliptic paraboloid. Right here, your denominators in that elliptic paraboloid are 1, right? Okay, so you have x squared over 1. I guess you can write that as 1 squared, and y squared over 1 squared. So that's definitely an elliptic. That's definitely an elliptic paraboloid. What about B here? So what sort of picture will we get from this? So again, let's just drop the function notation. So we have z equals x plus y. So that's not even second degree, because both of all of the variables are just raised to the first power, right? So that's just first degree. First degree equation. What is a first degree equation in 3 variables? What does that give you? That's a plane, right? So that's going to be a plane. Now we know all about this plane. We know what its normal vector is, right? What's the normal vector here? 1 minus 1, right? And what's a point there that's on this plane? All zeros, right? 0, 0, 0. So this plane goes through the origin. Okay. And there's its normal vector. Let's see. I think I have graphs of these two, A and B here. See if I can find them. There they are. So that's what we predicted, right? This is an elliptic paraboloid. We cut off there some of the sides of the elliptic paraboloid, but that is an elliptic paraboloid, and of course that's a plane. So the plane's sort of been trimmed there also on the around the edges to give it this nice what is that? Six-sided figure. Not a pentagon. What? Hexagon? Yeah, okay. And but still a plane, okay, because this really extends the plane really extends infinitely in other directions as well. All right, so that's pretty easy. Can y'all get this one for me? C. So what is C? So again, you can just drop the f of xy there, kind of in your way. And what sort of thing is that? Oops, I wrote it backwards, didn't I? Which makes very little difference. I'll find that on your, everyone got their cheat sheet here. Let me, while I'm thinking about that, let me start with the sheet. So what is that thing? Yeah, that's a hyperbolic paraboloid, right? Okay. That fits nicely. It looks exactly like that formula in the looks exactly like that formula in the table, right? Okay. So that's got a saddle shape to it. See, I graphed all of these, so let me see what that one looks like. So there it is. Okay. Yeah, that definitely fits that shape, right? Okay, that saddle shaped hyperbolic paraboloid. Let's see what D is here now. Okay. So this, all right, okay, we're gonna have to do a little manipulation with this equation. All right. So we have Z is equal to square root of x squared plus y squared. So that's really not a quadratic function, okay, because of the square root. All right. So technically, this is not going to be a quadratic function, but actually, when you graph it, you still will get a quadratic surface. Okay. Let me show you why. Because if you square both sides, right, you get z squared is equal to x squared plus y squared. And then if you subtract z squared from both sides, you get this. And then you can see, oh yeah, when I make this graph, I'm going to get a graph that that looks like this, the graph of this equation, right? But that is a quadratic equation. And what kind is that? Which one? Oh, an elliptic cone. Oh yeah, that's an elliptic cone. Exactly, right? Okay. Again, the A, B, and C squareds there are all one. All right. So we're going to get a cone. And I think indeed, when I graph this, this is what we got here. There it is. You can't see the bottom half though. Okay. All right. So that didn't graph, but there's the top half of that cone. You can't quite tell that's a cone, except you can see right here that it's coming down to a sharp point, right? Okay. So it is conical shaped. You sort of can get that a little bit, that impression, right, from the way this graph is drawn. Okay. By the way, what happened? By the way, what did happen to the bottom half of the cone? You can't see it in this. You cannot see it in this graph, but you might think, well, that's just because of the way you've chosen the portions of the X, Y, and Z axis I've chosen to draw, right? Because the Z axis here starts at 0. And so I'm not even seeing the bottom half of the Z axis. So maybe I don't see the bottom half of the cone. But I actually don't think the bottom half of the cone is even there. Why is that? Because look, don't think about this equation. Remember, the original equation is this one, right? Okay, Z equals square root of x squared plus y squared. And notice the square root of x squared plus y squared is always going to be what? Positive, right? Okay, and so this square root will also be positive, and so Z is never going to be negative, right? Z is not going to be negative. So the bottom half of the cone really isn't there. Okay, so see, that's what I was pointing. This is not really quite an elliptical cone, right? This is an elliptical cone. This equation is an elliptical cone, but this one's not quite an elliptical cone. But nevertheless, when you can figure out what the graph looks like by looking at squaring both sides. All right, you all try this one then for me. So what's this going to look like? So Z is the square root of 1 minus x squared plus y squared. And again, so technically Z is never negative there. Because square roots are not negative. But you don't need to think about that. Just try to figure out what that's going to look like. Okay, did y'all get something? One of these things? Which one is that one? Is it an ellipsoid? Is that right? How can that be right, Elijah? Sides. You squared both sides. Oh no, no. You're doing the other one. You're doing the wrong one. This one. Yeah. Okay. So now you spoiled the fun on this one. All right. All right. Well, let's try this one though, because I think your steps are very similar though. So you're going to square both sides, right? So you get z squared is equal to just all that's under the radical, right? Okay. And now just rearrange terms, right? So it looks like we would get what is it? Z squared. Am I writing that right? Plus x squared minus y squared is equal to 1. Oh, okay. So is that something? Which one? A one sheet. Okay. Oh, yeah, that's right. That's a one sheet hyperboloid, right? And what's the axis parallel to which axis x, y, and z is the axis of the hyperboloid parallel to? The axis of the hyperboloid is is that line that runs right through the middle of the line, right? Okay. So it is going to be parallel to the variable whose coefficient is negative, which in our case is y. So that axis of the hyperboloid is parallel to the y-axis. Let's see if that's the case here. So there's the hyperboloid. It's only the top half of it, though. Okay, and that again has to do with the fact that we had a square root, right? The z is only since the z was the square root, it can only be positive. So you don't really get the bottom half of this hyperboloid. All right, it's missing. So if you do the full hyperboloid, it would come around, on the bottom here, on the negative part of the z-axis. But unfortunately, since z was that square root, that part doesn't exist. But there's the axis right through the middle of the hyperboloid, right? And that is supposed to be parallel. Here's the axis right through the middle of the hyperboloid, right? Well, the axis is supposed to be straight right through the middle of the hyperboloid. And that is parallel to the y-axis, right? In this picture? Yeah. Okay. So, your axis runs through here, right? And that's parallel to the y-axis. Nice. Okay. So it looks like the last one is indeed, as Elijah spoiled for us, right? That is a what's that called? Ellipsoid, right? So it's kind of like a sphere, but it may be distorted, right? It may not be a sphere. Actually, this one may be a sphere. Yeah. Okay. Yeah, it's only half portion of a sphere. And again, that's because the way the equation was originally stated, right? Z is this square root. So square roots are positive. So you're not going to get any negative values for Z. All right. So so you're going to be missing the bottom half of the sphere. I don't know why my graphing gave this weird, looks like a melted sphere, right? Okay. The bottom half of it really is just a sphere, and the bottom half is missing from that sphere. The z cannot be negative. Let's see why this is the case, though. So just square both sides. So it's the same thing, right? Z squared is equal to 64 minus x squared minus y squared. Rearrange the terms, right? So you get x squared plus y squared plus z squared is equal to 64, and then divide everything by 64. So you get x squared over 64, but that's better known as 8 squared, right? So, and then y squared, 8 squared plus z squared over 8 squared is equal to 1. And then you can see, oh yeah, that definitely is an ellipsoid. And I believe since all these denominators are the same, it's going to be actually a sphere, okay? Not just a general ellipsoid, but actually a sphere. Okay. Now, it's hard, functions of two variables are already hard to graph and visualize, right? And I mentioned earlier, graphs of functions of 3 or more variables is essentially impossible. So let me show you a way that makes it a little bit easier sometimes to visualize what a graph of a function of 2 variables looks like without trying to construct that 3-dimensional surface. All right, and what we use is an idea called a contour map, and let me show you how a contour map works. All right, so what you'll do, it's essentially you're going to graph a trace, okay, a trace of the surface in a plane. All right, so what you do is you take the z and you set it equal to some fixed constant. All right. So when you do that, you get, so you take your z, just set that to constant, make that constant. So when you do that, you get, notice here, don't have any longer a function of three variables, right? Because the z is set as a constant. So what you really have is a function of two variables, which you can graph in two dimensions. Okay, you can graph in two dimensions. So that is called a level curve or a contour of the surface. What it really is a trace of the surface in one level of the z-axis. Okay, it's a trace in a plane running one level of the z-axis. So if you graph a bunch of these contours, a bunch of these level curves, notice those are two-dimensional curves, right? So you graph them in a plane. If you think about that properly, you get an idea of what the surface is going to be. Okay, if it were graphed in three dimensions. So again, this is just a way to make it easier for us to think about what a three-dimensional graph looks like without having to actually construct it in three dimensions. Let's take it. This kind of doesn't make sense until you see an example. So let's try this. Oh, let's take this one that we just worked with. Okay, so so when we graphed that right, we ended up getting that sphere, correct? So let me show you what a contour map of that sphere would look like. So again, the way you create a contour of the surface is you pick a value for z and you substitute it into the equation. An easy value to pick for z is so that's up. Let's try that first. Let's plug 0 in. Let's see. Okay. And of course, when you do that, just have an equation of two variables which you can graph. By the way, now when you set z equal to 0, notice what you're creating there is the trace of that surface. Trace of that surface when z is equal to 0. Of course, where is z equal to 0? That's the xy plane, correct? The xy plane. So what you're doing is creating the trace of this surface in the xy plane. Remember, the trace is the intersection of the surface with the xy plane. So we're looking at what's the intersection of the sphere with the xy plane. Well, of course, when you intersect a sphere with a plane, or you have a sphere, imagine like this sphere, cut through that with a plane, right? What's that cross section going to be? A circle, right? Okay. So what we're going to be graphing here is a circle in the xy plane. That's the intersection of the big sphere with the xy plane. Easy to verify that this is a circle. Just do the algebra to see this, right? So you just set z to 0. So you get 0 equal this square root. And then, of course, you're going to square both sides, right? Just like we did before. Of course, when we square 0, doesn't amount to anything, right? So we get this. And then, just move the x, y terms to the left-hand side. So you get x squared plus y squared is equal to 64, right? And you definitely know that's a circle, right? And write this as x minus 0 squared plus y minus 0 squared is equal to 8 squared. So not only is that a circle, that's a circle that's centered at the origin, 0, 0, and its radius is 8, right? The radius is 8. So when you plot that in the xy plane, you just get, see if I've got it here. Oh yeah, you get this big circle. The big circle on the outside. That corresponds again to the contour or the level curve where C is equal to 0. What you're really, there's our graph. of that contour. It's a circle on the outside, big circle on the outside. What we really graph, though, is, and it's the trace of the sphere in XY plane, right? That sphere intersected the XY plane in this circle. But we're not going to try to graph this, okay? Because this is in 3 dimensions. But this is just an illustration. You create a contour map, all you graph is 2 dimensions. Okay. So that curve in 2 dimensions, just like the graph in 2 dimensions. Now, to get but what we're trying to do with the contour map, though, is get a better impression of what the surface looks like in 3 dimensions. So what you can do is choose different values for that C. Instead of 0, you can other values for C. Okay. So of course, what happens when you choose different values for C? Let's let C be 6. What happens in that case? So I'd have 6 is equal to the square root of, what was it, 64 minus x squared minus y squared, right? So square both sides, we get 36 is this. You just get a smaller radius, right? So you get x squared plus y squared is equal to, what's 64 minus 36? Is that 28? And so you have a circle, again, with center at the origin, but the radius is now the square root of 28, whatever that number is. A little bit bigger than 5, right? So your radius is now the square root of 28. So again, that when you graph that curve, you get what's called a level curve or a contour or a forgot the other term. There's a more archaic term, isobar, okay, of this surface. Let's see, where is that right here? C, that was C equals 6. So if we look at our picture, oh, it's this circle. But what we had really graphed is this cross section of the sphere, right? Okay, we graph this cross section of the sphere. That's the intersection of the sphere with what plane? It's not the XY plane, but when you graph this contour, this trace, you're intersecting the sphere with what plane? The plane where z is equal to what? No, you're intersecting it with the plane z equals 6. That z equals 6 is a flat plane, okay? It's just a horizontal plane where z is exactly equal to 6, okay? I'm pointing here, yeah, where z is exactly equal to 6. That's just a flat plane. And so when we graph this contour, we're just graphing the intersection of that sphere with that flat plane z equals 6, that trace. But we put all of those, so when we create a contour map, we put all of those traces, all of those level curves or contours on one XY plane, and that gives us kind of a visualization of what that surface is going to look like. Does that help you understand that surface? If you know those are contours? Maybe a little bit, okay? Maybe you can understand, oh, all right, so that surface is going up, right? The traces of the surface are all circles, so that surface has to be a sphere, okay? Coming up to, by the way, what's the height of the sphere on the z-axis there? It comes up to 8 on the z-axis, right? Is as high as it goes. Notice the contour, when you intersect the surface with z equals 8, you just get a single point, right? When you intersect that surface with the plane z equals 8, you just get 1 point, right? There's only one intersection point there. Okay. So again, what's the idea of contour maps? Just so that we don't have to create 3-dimensional pictures, all right? We can try to get an idea of what a surface looks like by just creating two-dimensional curves, right? Ooh, let's try another one. Y'all are gonna have to help me. Well, I've already cheated there. I gave y'all some ideas here. Okay. So suppose you're trying to graph z f of xy equals y squared minus x squared. So if we put a z on there, we would have z equals y squared minus x squared. So is that, what is that thing? Is that that's a hyperbolic paraboloid, right? Okay, that's what that creature is if you look at the quadratic surfaces. All right, and there's an actual graph of that hyperbolic paraboloid, right? You got that nice saddle shape there, right? So let's think about the contours, though, the level curves, and always nice to think about the simplest one, the trace in the xy plane. So if you take this hyperbolic paraboloid and you intersect it with the xy plane, what sort of a picture are you going to get? Can y'all see that trace in the xy plane there? It's, man, can I see it there? I'm not sure. I think it's this and this. That's part of it, okay, in front. What sort of thing is that? Oh no, let's look. All right. So so when you're trying to discover one of the contours or one of the level curves, right? Again, you just choose a value for c and set z equal to that. So for the xy trace, you're going to set z to 0, right? So you would get 0 is equal to x squared, I'm sorry, y squared minus x squared, or better known as x squared equal y squared. And man, what is that? Almost, almost, Elijah. Okay, you have to remember these things are squared. So when you take the square root of both sides, you're going to get x is equal to plus or minus y. Okay. It might have been easier if I wrote it this way: y equals plus or minus x. That's the same thing. Okay. So when you graph this, the trace in the xy plane, notice you get two things here: y equal plus x and y equals minus x. What does y equal plus x look like? That's just y equals x. What is that line? Oh, it's just like this, isn't it? Isn't that the line y equals x? So you get this line. And then y equals minus x is also the same line, except with slope -1. So it goes downhill from left to right like this. Oh, so interesting. So when you intersect this surface with the xy plane, you get just these two perpendicular lines. Okay, those lines are perpendicular to each other. That's kind of what you can see here, right? There's half of it, of the trace, and then there's a half in the back as well. You can almost see it. It's this and this in the back there, that X shape, okay? Now it gets a little bit more fun when you pick different values for z other than 0. So here's with c equal 4. So you get 4 equal y squared minus x squared. And now you have to dig through your pre-calculus memory there to think about what is the curve y squared minus x squared. All right. That is it's not a circle, right? If there were x squared plus y squared equal 4, that would be nice, okay, because that's just a circle. But you got subtraction there, y squared minus x squared. What is that? That turns out to be a hyperbola. So when you graph it, you get a picture like this, okay? So you get these two branches, right, of the hyperbola when you graph y squared minus x squared. So it ends up looking like this. You might be wondering, this finally answers the question, Why were we thinking about hyperbolas in pre-calculus? Well, one reason is because notice this contour of this quadratic surface, right, in 3 dimensions. That contour, that level curve, turns out to be a hyperbola. All right, so it's nice to know what the graph of that equation looks like in 2 dimensions. Okay, because that's the contour trace of a 3-dimensional surface, right? All right. If you do the contour map for many different values for C, not just 0 and 4, here's the entire contour map, okay, for that 3-dimensional surface. So does that give you some sort of idea of what it's like? Maybe. There we go. 7 or so. See, get a bunch of different. Same. That's why. Okay. One last thing here, and before we just general topic about functions of 2 variables. I mentioned, right, they have domains, and we do have to be careful sometimes about domains of functions of 2 variables. So let's just look at a couple of examples where we're asked about the domain. So, I mean, this is a very straightforward question like this. So this looks very much like a college algebra question. Find the domain of this function, right? So because this is a function of 2 variables, remember, inputs are points in the xy plane, right? So when you find the domain of this function, you're going to be finding a region of points in the xy plane. What points can you use as inputs to this formula, right? Okay. Many times the domain will just be the entire xy plane. Okay. Just like for functions of 1 variable, many times the domain is all real numbers, right? The whole x-axis. So many times for functions of 2 variables, the domain will be the entire xy plane. So that's our nice easy instance. Okay, but I don't think for this function the domain is going to be the entire xy plane. Because, of course, what's the issue in this formula that could be messing you up? The square root, right? We don't want to be taking square roots of negative numbers, correct, right? So we have to be careful to make sure that the radicand, the quantity under the radical there, is not negative, right? So we want it to be positive. We want that to be positive. So we have to figure out what values for x and y are we certain will make this quantity positive. Or at least not negative. Doesn't have to be positive, but not negative. Well, you know the way to attack this, right? Is don't worry about the inequality at first. Let's just turn this into an equation and see if we can figure out what this equation looks like. Okay, all right. So what values of x and y are going to make this exactly equal to 0? Exactly equal to 0 is greater than or equal to 0, so that's good enough, right? Okay, so that would only be part of the domain, though, right? The domain would be much larger, but this is part of the domain. So let's see if we can figure out what this curve looks like in the xy plane. Oh, I bet we can figure that out pretty easily, right? But this is a minus here, right? So if you just adjust terms, right, rearrange terms, you would have 16 is equal to 4x squared plus y squared, right? And now divide, what do I want to do there? Divide everything by 16. Let's try dividing everything by 16. So you get 1 is equal to x squared over 4 plus y squared over 16. And you know that, let's rewrite that a little bit. That's x squared over 2 squared plus y squared over 4 squared. So you have 1 is equal to x squared over 2 squared plus y squared over 4 squared. Do you know what that sort of curve is? It's not quite a circle. It's an ellipse, right? Yeah, not an ellipsoid. This is just a plain old ellipse. Okay, that's going to be an ellipse, right? Okay, and the intercepts are very easy. The x-intercepts are going to be 2 and -2. You can read those out of the denominator. So the x-intercepts are going to be 2 and -2, and the y-intercepts are going to be 4 and -4. And once you've got the intercepts, this thing is centered at the origin. So because this is x minus 0 squared, y minus 0 squared. So this is centered at the origin. So you get a nice, just a nice ellipse like this. Oh, shoot, I almost was drawing it good. And then my old age caught up with me there. My hand started shaking. So let's, well, that's pretty pathetic ellipse, but kind of looks like an ellipse, right? So that's part of the domain. That curve is part of the domain. We have to figure out where the rest of the domain is. Look, well, look, it's either going to be inside the curve or outside the curve. It's going to be the rest of this domain. All you have to do is test a point either inside or outside the curve. You pick one that you like. What point do y'all want to test here? Make it easy now. Don't pick 100, 100 or something. I don't want to test that. Easier. Even that's too difficult for me. 0, 0. There we go. Right. Okay. So try 0, 0 and see if that's a solution to your original inequality. Does 0, 0 a solution to this inequality? If you plug 0 in for x and 0 in for y? It is, right? 16 minus 4 times 0 squared minus 0 squared. I think that's 16 minus 0, right? Which is greater than or equal to 0. Oh, so the origin is a solution. That means the origin is in the domain. And so there you know what the rest of the domain is there. It's everything inside of that ellipse. Everything inside of that ellipse is the domain of that creature. No, okay? Because what's going to happen, Elijah, if you pick anything out of this region, plug the x and y coordinates in, this radicand will turn out to be non-negative. Do you not trust me there? Yeah, try 1, 1, for instance, right? That's definitely in that region, right? Plug 1 in for x and 1 in for y. You're going to get 16 minus 4 minus 1. So I think that'll be 11, right? But square root of 11 is positive. So you're okay, right? Okay. What you're asking about is the z's have to turn out to be positive. So when you plot this, remember, this is a surface, right? So when you plot this surface, you're going to end up with a surface above this portion of the xy plane. It'll be above this portion of the xy plane, right? So you'll have a surface above this portion of the xy plane, but you won't have any part below the xy plane because the z cannot be negative. The z can't be negative. Actually, this is what we graphed already, wasn't it? Didn't we graph this one a moment ago? Was that this? Was that this one? No. No, okay. I don't think I have a graph of this one, so we cannot see it. Darn it. Okay. So indeed, when you graph the entire function, you will get a surface, three-dimensional surface, but that surface will only exist above this portion of the xy plane, not below it, because the z cannot be negative. All right, I'm gonna let y'all try one. So I have no idea what happens when you graph this, because I don't have a graph of this. Maybe we'll try graphing this in a moment and see if we'll see if Wolfram Alpha will graph this for us. All right. So, but I want to know is what's the domain? So what points can you use as inputs? What points in the xy axis can you use as inputs for this function? So notice you kind of have the same situation that we had in this example, right? You have to worry about the radicand. The quantity under the radical has to be non-negative, right? So the x squared plus y squared minus 9 has to be greater than or equal 0. But you have another little complication here. You're dividing by x, and that also can throw off your domain, remember? Because y. Yeah, it cannot be 0, right? So the x cannot be 0 either, right? So see if you can plot the region where this is non-negative, and then think about excluding where x is 0. Of course, where is x 0? I'm going to graph that on the xy plane. So where is x 0? Well, at the origin, but where else? X is 0 in lots of places. Where else? Not the x-axis, the y-axis, right? Okay, so yeah, that's right, right? The y-axis, right? Every point on the y-axis, x is 0. So it looks like the y-axis is going to be completely out of our domain. The y-axis cannot be in. So you're missing, in addition to missing some other things, because of that numerator, you're missing the entire y-axis. That cannot be the domain. All right, so y'all work on that, okay? Think about the top there. Where is that non? And what is that? So set up an inequality. Yeah. So graph that circle. You're going to graph that. Just scribble x y axis. You don't have to make it perfect. So rest of that circle. That circle. Test. Test. Test the point. Smith is square. Start. Yeah. Single cat. Start. Start. Just think about so that's a lot. Oh, oh, nice. Now, this is missing. Set. Pure. Simple. Hard. Take back this. Sure. Back. So now you start. I didn't say. Yes, that does look this. So this circle, kind of, where's the rest? So you see it. Yeah. So by the now, so that means outside. So what's your outside circle? Purple. So, so that circle. So, so other. So 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 it's not so okay. So switches this circle. Just test it. Picking this one, fine. But square root two minus 9 is so out one. So it's not inside the circle. So reshape. So yes, so yeah. All because remember, turn your okay. Yeah. So back. So, so all that. So yeah, no, Yeah. Don't worry about it. There. Don't worry about writing it set. There we just have a picture of it. Perfect. Try to play that circle. So everything. It's not going to change. You have to graph that. It's like, so, yeah, so graph the circle. So that's the place to start. Okay. All right. All right. So most people got to the right place there. Okay, eventually. Look, so as we discussed, right, you have to make sure that the radicand is non-negative, right? So the x squared plus y squared minus 9 has to be greater than or equal to 0. So you're trying to figure out where are the solutions to that? Where are the solutions to that inequality? Well, start by making it easy on yourself, right? Don't worry about greater than or equal to 0. Just worry about plain old equal 0, okay? And try to figure out the solutions to that equation. That's a curve that we sort of understand, right? The solutions to that equation is a curve we sort of understand. This is x squared plus y squared equal 9. And that's a circle, right? Its center is at the origin, and the radius there is 3. So, so you just try plotting that circle. So you graph that, you get a circle that looks like something like this. There's a really ugly graph, right? Okay, but you get that circle. But that's not your entire domain, right? Okay, your domain includes a lot more points on the xy plane. So to find the rest of those points, just pick a point inside or outside of the circle and test it. An easy one to pick again is the origin. So if you pick the origin and put 0, 0 into this inequality, what happens? You get 0 squared plus 0 squared minus 9 is greater than or equal to 0. And that says minus 9 is greater than or equal to 0, which is not true, right? So the origin is not a solution to the inequality. That means that the real solutions to the inequality are outside of the circle. That's an easy way to solve inequalities, okay, like this one. So that means that we want all of these points, we'll shade in this region outside of this circle. So when you plot this surface, in 3 dimensions, not the inequality, right? But when you plot the original function in 3 dimensions, it's only going to exist, right? That surface is only going to exist above or maybe below this portion of the xy plane. It's going to have a big hole in it right here, okay? By the way, that would happen. I think that would happen if the surface were what is that? One of these things, okay? Wouldn't that give you a domain like this? I think so. What's that? Hyperboloid of one sheet. Maybe another one would work too for this. I don't see another one. So, well, anyway, there's one possibility, right? Okay, maybe the surface looks like a hyperboloid of one sheet. Now, there's one other little exception here, though. That denominator x. You remember x cannot be 0 because you'd end up dividing by 0. Well, where is x0? Along the y-axis, right? So that means that the y-axis not in your domain. So this portion of the y-axis above the circle, this portion of the y-axis below the circle, it looks like those should be in the domain, but they're really not, right? Because you're dividing by x. So you have to kind of indicate that in your picture. It's hard to do. Sometimes you do that with just make a dashed line here. So you might turn your axis into a dashed line. And sometimes that is used to indicate that the line there is really not part of the domain. Okay, that's you really have to squint to see that. That y-axis above and below the circle, not part of the domain. Of course, the y-axis inside the circle also not part of the domain as well, right? Okay. Now, so before we quit, let's at least here take a start at what we're going to do with functions of two variables. Now that we have just a little taste of them, and so we're going to apply calculus to these functions of two variables, and so we're going to be asking questions about functions of two variables, very similar to the questions, well, actually identical almost to the questions that you ask about functions of one variable in calculus 1 and calculus 2. Now, actually, we're going to start with differential calculus. So we're going to ask a differential calculus type questions about these functions of one variable. So, so what sort of calculus questions did we ask about functions of one variable? One key thing we want to know about functions of one variable, but also functions of two variables is the function continuous? Okay, so is the function continuous on a particular portion of the domain? Okay, so over a particular portion of the domain, is the function continuous? Now, so we have to remind ourselves, what does a continuous function for one variable mean? What did continuous mean in calculus 1? You recall? So what made a function, just in rough terms, what made a function continuous? That is differentiable. Okay, so but not quite the same as. All right, that's what. So yeah, remember if you had a sharp corner point on a graph of a function, that means it did not have a derivative that sharp. That means it's not differentiable. But so differentiable for basic that's no breaks, right? That was a key thing, right? No breaks, no holes, right? No gaps in the curve when you graphed it is what made it continuous. This is exactly the same idea in 3 dimensions, okay? So in 3 dimensions, when you graph a function of 2 variables, of course, you get a surface, right? So for the surface to be continuous, you do not want breaks or holes in the surface, right? Okay, that's what makes the function continuous. So you have to have a solid surface, right? Okay, without breaks or holes or gaps in it, right? Here's an example of that in 3 dimensions. So you see this this surface not continuous at 0, 0, okay? Because you've got here a hole in the graph at the origin, okay? See at the 0, 0, right? On the xy plane at that input, you get a hole there in the graph, right? In the surface. And so we would say that this function of 2 variables not continuous at 0, 0, okay? Here's a continuous example on the other hand, right? Looks kind of the same, but see, notice at 0, 0, no hole or break there in the surface, right? So when you get kind of a solid, complete surface, we say that that is a continuous function of two variables. Okay, there it is, right? Continuity over a region means what you might expect. The surface above the region not have any. Now, that is the informal definition of continuity, but there is a formal definition of continuity, a mathematical definition of continuity, because these terms, like holes or breaks, are not exact terms. So we can take that notion of continuity, this informal notion of continuity, and we can formalize it into mathematical language to make it rigorous. We'll show you in a moment here or a little bit later, what the exact mathematical definition of continuity. Okay. So what else did we concern ourselves with in differential calculus? Not integration, right? But in differential calculus, not integral calculus. What other sort of questions were we interested in functions of one variable? Yeah, slope of the tangent line, right? Because what did the slope of the tangent line tell us about the function, though? What? Yeah, well, yeah, whether it was differentiable, right? If the slope of the tangent line existed, that means the function was differentiable at that particular point where you're finding the tangent line, right? But what sort of questions did you answer about the function using the slope of the tangent line? So what did the slope of the tangent line tell you about the function itself that was useful? Oh, increasing, decreasing, right. Okay. Remember, if the slope of the tangent line was positive, that means the curve was increasing, right, from left to right at that point. If the slope of the tangent line was negative, that meant the curve was decreasing from left to right. Okay. So we're interested in whether a curve is increasing or not. Okay. That's an important question in differential calculus. Okay. Now, the same sort of question you want to answer in 2 dimensions, okay? I mean, in 3 dimensions. We want to know, is the surface going up or is the surface going down? Okay, is the surface increasing or is the surface decreasing? Now, however, okay, that's a really tough question in 3 dimensions, okay? Because in 2 dimensions, right, you only have to think, if I'm going from left to right, along the x-axis, so if I think of myself as traveling from left to right with respect to the x-axis, is the curve going up or is the curve down? Right? Okay. You're always thinking of moving from one direction along the x-axis. Unfortunately, in 3 dimensions, things get infinitely more complicated. Okay. You have to think about in what direction you're moving toward a point, okay? And it may not be just left to right, okay? You can be coming from any direction. You can be coming from any direction. That means you can be coming from infinitely many directions, okay? You may be coming from infinitely many directions. And you have to think about, okay, if I'm coming from a particular direction on this surface, so if I'm traveling on this surface in a particular direction toward a point, am I going up or am I going down? Okay. But if you're going in another direction, you may be going a different way. Okay. So in one direction, you may be going up. In another direction, you may be going down. You may say that's not possible, but I think you've already seen an example of this. Let's take a look actually at one of our pictures here. Oh, here's a good one. Okay. Look, if you were think about this, what was this thing called? Yeah, it's a saddle, a hyperbolic paraboloid, something. Hyperbolic paraboloid, right? Okay, so let's think of ourselves right here. So if you are moving toward the origin on this surface, if you're moving along the x-axis, right? Okay, so if you're moving in the direction of the x-axis toward the origin, how are you traveling? Are you going up or are you down? Going up, and then of course, right there, continue along in the direction of the x-axis. On the other side, you'll start going down. right? Okay, but what if you're coming in this direction, parallel to the y-axis? What's happening? Ah, okay, so it's different. That makes it way more three-dimensional. Whether you're going up or down on a surface depends on which direction. As you're traveling, if you're moving toward a point on the surface, right? Whether you're up or down, change, right? Which direction you're so. And unfortunately, in three dimensions, you can be moving in infinitely many directions toward a point, right? Not just left or right, but lots of different ways going toward a point. So that gets harder. But that's one of the things that we want to consider, okay? Is if we're going, how the surface is moving, right? Is the surface rising or is the surface falling at a particular point? And finally, one other thing. So what was the other thing? After increasing, decreasing, what else did you think about in about functions in differential calculus? What is negative or positive? Oh, the output is negative or positive? Yeah, that's important, but that's not really a calculus question. That's more of an algebra question, actually. Okay, so you don't need calculus to answer that question if the if the output's going to be negative or the output's going to be positive. Yeah, what's that called? It's from the second, it's concavity, right? So another thing we're concerned with for curves is their concavity. That's the shape of the curve, right? Okay. We're going to be also concerned with that question for in two dimensions, the curvature of a surface or the shape of the surface. Okay. Basically, it's kind of similar, very similar to two dimensions. If you have a surface, is it curved down like this, right? Okay, so do you have an inverted bowl or have a surface like this, right? So do you have a hill or do you have a valley? Okay. Say, yeah, opening upward or opening downward. Of course, if you have a plane, neither one, right? Because that has no curvature at all. Right? So planes don't have any curvature. Of course, in two-dimensional space, you have lines which also have no curvature, right? Okay. What's the concavity of a line that has no curvature? Its concavity. Zero, right? Okay. Yeah, if you measure the concavity of a line, you get zero, right? Because it has no curvature, right? Well, planes have no curvature either, right? Okay. Also, so you can have that same analogous idea for in three dimensions that you have in two dimensions. Okay, all right. So those are the questions that we're going to take up. All right, and in 3D calculus, exactly the same things that we did, exactly the same questions that we considered in, exactly the same questions that we considered in calculus. Right, just apply those to three dimensions, and just keep in mind, whoops, things are going to be complicated because we have a lot more directions to approach a point in three dimensions than we do in two dimensions. Okay, so that makes things tougher. All right, to think about. All right, so first thing we want to take up is continuity. So what does it mean technically for a function of two variables to be continuous? All right, so we described it informally. You're not going to have any holes or breaks, right, in the surface. That makes it continuous. All right, but again, a hole or break, that's an informal term. So mathematically, in a rigorous mathematical form, what does it mean for a function of two dimensions to be continuous? Okay, I am certain that you have forgotten this for functions of one variable. Okay, the formal definition of continuity for functions of one variable. All right. So I know you've completely forgotten it. So this will be like relearning it for two variables. But the two variable definition is very similar to the one variable. So if you learn the two variable definition, you will you'll have also mastered the one variable definition as well. Okay. All right. So, but we're going to stop there because this requires some explanation. Um, the, uh, the formal idea of involves limits. Remember, limits are calculus, right? Okay. Well, one of the reasons you learn limits in calculus is to help understand the definition of t. And so limits also play a part in formal definition of t and for functions of two variables as well. Okay. So we have to first we have to remind ourselves about limits and we're going to be dealing with limits in three dimensions rather than limits in just in two dimensions. Okay, and so those are more complex too. But the idea is very simple. Right? So so we don't want to get into this examples of this definition yet. We'll save that for next time. Okay, but that's where we're headed, right? On Monday. Okay, so I'm going to stop there. All right, and what homework? Let's see where we're at on the homework there. Okay, well, I think you can get. Oh, this homework is yeah, you won't have this. This homework is easy, and I think you can probably maybe start this homework, but won't be able to, I think, complete that one yet until Monday's lecture. Okay. Well, once we learn about continuity, and then we're there, start talking about surfaces increasing and decreasing in three dimensions. So we'll be right with calculus at that point. Okay. I'll see you guys on Monday then.